Okay, let's dive into something that honestly feels a bit like magic with large language models. In context learning, or ICL.
It really does.
You give the model just a few examples in the prompt, say, sea otter translates to litre mag, cheese to fromage, pepper to.
And boom, it gives you poivre.
Exactly. It learns the task like instantly, right there, without any fine-tuning or changing the model itself.
And that's the crucial bit, isn't it?
Yeah.
The model has billions of parameters, and they are fixed. They don't change during this process.
Mm.
So the learning, this apparent learning, happens in a single shot, just during inference.
So the central mystery we're tackling today is how? How does a neural network with frozen weights learn a new rule, a new function, just from the prompt?
Right. And the research we're looking at goes beyond just saying, wow, look what ICL can do. It's asking how it does it, mechanistically, algorithmically.
Okay, so what's the mission for this deep dive?
The mission is really to unpack this. We're exploring the idea that these transformers aren't just acting like you're learning. The hypothesis is they are actually implicitly running well-known learning algorithms. They've sort of learned how to learn already.
Okay, that sounds like meta-learning, learning to learn.
It absolutely is, but it's an implicit kind. Standard meta-learning often have these explicit inner and outer optimization loops.
Right.
With ICL, the thinking is that the massive pre-training phase, where the model sees just tons and tons of data, acts like the outer loop. That's where it figures out a general strategy for learning.
Okay.
Then when you give it those examples in the prompt at inference time, that forward pass acts like the inner loop. It executes that learn strategy on the specific task you just gave it.
So pre-training basically turned the model into a general-purpose algorithmic executor, like it learns statistics.
That's a good way to put it, yeah. And to really get a handle on this, the researchers used a framework from cognitive science, David Marr's levels of analysis. It's super helpful for breaking down complex systems like this.
Okay, Marr's levels. Remind us what those are.
Sure. So level 1 is the computational level. That's the what's the overall goal? Like maybe it's minimizing prediction error or finding the best fit line.
Got it. The objective.
Level 2 is the algorithmic level. That's the how, what's the actual recipe, the step-by-step procedure being used. Think gradient descent, or maybe calculating a matrix inverse. The specific algorithm.
The process.
And level 3 is the implementational level, the with what. How is that algorithm physically carried out? In our case, it's down to the nitty-gritty of the transformer's architecture, the fixed weights, the activations flowing through the layers.
What, how, and with what makes sense. So before even seeing what algorithms the models do learn, the researchers first establish what they can theoretically do, right? Using linear regression as a sort of test case.
Exactly. They needed to show that the basic building blocks, the self-attention mechanisms, the feed-forward networks, have the necessary tools to actually implement these algorithms.
And could they?
Yes, but how efficiently they could do it, the sort of cost, varied a lot depending on the type of algorithm.
Okay, like take gradient descent. That's an iterative approach, step-by-step improvement.
Right. And implementing gradient descent, or GD, turns out to be relatively cheap in terms of the model's width, the size of the hidden state.
Yeah.
You only need capacity that scales linearly, like mapcality, with your input dimension dialer. But because it's iterative, taking many small steps, it demands depth. You need a deep model, lots of layers stacked up to actually perform all those sequential updates.
Okay, so deep and maybe narrower models are suited for iterative things like GD. What about the opposite, like a direct closed-form solution, calculating the answer in one go?
That flips the resource requirement. If you want to compute a direct solution, like using matrix inversion for regression, that's much more expensive in terms of width.
How so?
Well, the math involves manipulating potentially large matrices, like del times D matrices. To store and operate on those, the research suggests you need model width that scales quadratically with the input dimension, D22. So you'd need a really wide model, maybe not necessarily as deep.
Wow. Okay, so the architecture itself isn't just providing general smarts. It's actively biasing the model towards certain types of solutions.
Precisely. That's a key takeaway about architectural bias. A deep, narrow model might naturally prefer or find it easier to implement iterative algorithms. A wide, shallow model might be better suited for these big one-shot matrix computations. The design itself shapes the algorithmic possibilities.
That's fascinating. Okay, so the theory shows what's possible and how architecture influences it. Let's switch to the experiments. What happened when they treated the transformer like a black box and just looked at its input-output behavior? What algorithms did it seem to be running?
The findings here were pretty remarkable, especially in the linear regression setting. In the simplest case, the noiseless regime where the examples in the prompt perfectly describe a linear function.
Like points exactly on a straight line.
Exactly. In that case, the transformer's predictions were statistically identical to ordinary least squares, OLS regression.
OLS, that's the standard textbook method for finding the best fit line by minimizing squared errors. That feels right.
It does. But here's where it gets really interesting. They tested it in an underdetermined setting. Fewer examples in the prompt than dimensions in the input data.
So infinite possible lines could fit the data points.
Right. And out of all those possibilities, the transformer consistently implemented the minimum norm OLS solution. It didn't just pick any solution, it picked the mathematically simplest one, the one with the smallest weights. That shows a very specific, non-trivial inductive bias learned during pre-training.
Okay, that's impressive for clean data, but real data usually has noise, right? What if the examples aren't perfect?
Great question. They tested that too, adding Gaussian noise to the context examples. And as you'd expect, the optimal strategy changes when there's noise. You don't just want to fit the data perfectly anymore because you might just be fitting the noise.
Right, you need to regularize somehow, prevent overfitting.
Exactly. The statistically optimal approach in this noisy scenario, assuming Gaussian noise and priors, is called the minimum Bayes risk predictor.
Okay, that sounds complex. What does it boil down to algorithmically?
Well, for this specific setup linear function, Gaussian noise, the minimum Bayes risk predictor, is mathematically the same thing as ridge regression.
Ridge regression, so that's OLS, but with a penalty term added to keep the weights from getting too large.
You got it. It adds that lambda regularization parameter and the transformer's behavior. It perfectly matched ridge regression.
Perfectly.
Yes, and even more precisely, the amount of regularization it implicitly applied corresponded exactly to the theoretically optimal value, the ratio of the noise variance to the prior variance,
Yeah.
sigma toto. It's a really powerful convergence. You have one theory saying the transformer implements algorithms like ridge regression, and another theory framing it as implicit Bayesian inference, and they both land on the exact same mathematical description, which is then verified by the experiments. It suggests these are two sides of the same coin.
That's a very strong piece of evidence, but let's connect back to the architecture. You said depth is needed for iteration. Did they see the type of algorithm change if they limited the model's depth?
They did. It wasn't just that performance got worse with fewer layers. The kind of algorithm the model seemed to be implementing actually changed. They observed clear algorithmic phase transitions.
Phase transitions, like sudden shifts.
Yeah, exactly. So with really shallow models, maybe just one or two layers deep.
What did they do?
The best description of their behavior was just a single step of gradient descent, like the most basic update possible. They just didn't have the sequential depth to do anything more complex.
Okay, one step, then add a few more layers.
Moving to medium depth models, say 2 to 4 layers, gave it enough computational room to find a more stable solution. And its behavior snapped into matching ridge regression.
The regularized solution.
Right. And only when they used deep models, 8 or more layers, did the behavior fully converge to the standard ordinary least squares, OLS solution, the minimum norm one in the underdetermined case.
So increasing depth is literally like giving the model more time, more sequential steps to run a more sophisticated algorithm.
That's exactly the implication. You're not just adding parameters, you're adding the capacity for sequential computation, allowing these iterative algorithms to unfold.
Okay, this is compelling behavioral evidence, but it's still black box, right?
Yeah.
How did they try to confirm if these algorithms were really running inside step by step? Did they look at the implementation level?
They did. They used techniques called probing to try and decode intermediate values from the model's hidden states.
Yeah.
For OLS, there are specific quantities you need to compute along the way.
Like what?
For instance, you need to compute something called the moment vector, which is basically math BFX, top math BFY, and eventually you use that to get the final OLS weight vector, math BF the OLS. They probed the activations at different layers to see if and when these vectors could be accurately read out.
And could they? Did they appear sequentially?
Yes, and that's the key. They found that the moment vector could be reliably decoded from relatively early layers, maybe layer 7 in their setup, but the final OLS weight vector, which depends on the moment vector, only emerged clearly much later, around layer 12.
Ah, so it confirms a temporal pipeline. Step 1 happens early, step 2 happens later.
Exactly. It's strong evidence against simple mimicry and supports the idea of a sequential computational process unfolding layer by layer, mirroring the steps of the actual algorithm.
And how are these vectors stored? Just like variables in memory?
Interestingly, no. They found that nonlinear probes were consistently better at decoding these vectors than simple linear probes were.
Even though the vectors themselves are linear concepts.
Right. It suggests these quantities are represented in a nonlinear, distributed way across the hidden state activations. This might be how the model gets around that theoretical mathematical width requirement for storing matrices. It uses its nonlinear capacity to encode things more efficiently.
Okay, so the model seems to be implementing the steps sequentially, encoding the intermediate values. It really looks like it's running OLS. But there's always a but, isn't there? Is it truly implementing the abstract mathematical algorithm?
This is where the story takes a critical turn. A study by Hill and colleagues really challenged this notion. They asked, is it executing OLS in general, or just a version that works for the kind of data it saw during pre-training?
How did they test that?
They used out-of-distribution, OD data. They trained the model on linear regression tasks, where the input data points always lay in a specific subspace, like a particular plane in 3D space. Then they tested it on data that was mathematically identical in terms of the linear relationship, but the input points were rotated into a completely different orthogonal subspace, something it had never seen the likes of during training.
And for a true OLS algorithm, that rotation shouldn't matter, right? The math is coordinate independent.
Precisely. A proper OLS solver would perform identically. But the transformer?
It failed.
Its performance absolutely cratered. It fell apart on the OD data, even though it nailed the in-distribution version.
Wow. So it learned the algorithm, but only for the specific statistical patterns it was trained on.
That seems to be the refined conclusion. It's not learning the abstract general OLS algorithm from a math textbook. It's learning an incredibly effective computational shortcut, a kind of heuristic that perfectly mimics OLS on data that looks statistically similar to its training data.
That shortcut is brittle. It breaks as soon as the data distribution shifts significantly.
Exactly. It highlights a potential gap between mimicking performance on familiar data and possessing robust, generalizable understanding.
That's a huge caveat. Okay, so far we focused heavily on linear regression, where attention mechanisms seem key. But ICL works for complex, nonlinear tasks too. Where does that power come from if attention is fundamentally linear?
That's where the other main component of the transformer block comes in. The feed-forward network layers, the FFNs.
Right, the MLP layers between the attention block.
Yes. Research shows that if you try to do nonlinear ICL tasks using a transformer with only linear attention, like if you remove the FFNs or made them linear, it basically fails. It can't do better than a simple linear predictor.
So the FFNs are providing the nonlinearity. How?
The hypothesis, which has good support now, is that the FFNs act as powerful nonlinear feature extractors. During pre-training, they learn to take the raw input data and project it into a much higher dimensional space.
And in that higher space,
the complex nonlinear relationships in the original data become, effectively, linear. The FFNs learn to untangle the data.
Ah, I see. So the FFNs do the hard work of feature transformation, creating a space where the problem looks linear.
And then the attention mechanism can just do its linear fitting trick, like OLS or Ridge, within that learned feature space.
So for nonlinear tasks, ICL is basically performing kernel regression implicitly.
That's the perfect way to summarize it.
Yeah.
The FFNs learn the kernel function on the fly, tailored to the pre-training data. And attention performs the linear regression in that kernel-induced feature space.
Okay, pulling all these threads together, ICL starts to feel much less like magic and more like, well, like computation. It's an emergent process where the model executes implicit algorithms, OLS, Ridge, GD, kernel regression that mimic classical methods, but crucially are highly optimized for and potentially brittle to the statistics of the training data.
Exactly. And this understanding gives us some really practical takeaways. For you, the listener, navigating these models, here may be 4 key things to keep in mind. First, ICL is implicit algorithm execution. Start thinking about ICL behavior using the language of these algorithms. Is the model behaving like it's doing OLS? Is it regularizing like Ridge? Is it taking iterative steps like GD? This can help predict or understand its behavior.
Makes sense. Second takeaway.
Second, beware distributional shifts. Remember the OGI experiments. Just because a model aces your test cases that look like its training data doesn't mean it will generalize. Be skeptical of performance on data that's statistically different. That mimicry can be fragile.
Crucial point. Third,
Prompting is algorithm steering. Those examples you provide in the prompt, they aren't just vague guidance. They literally form the input data set for the implicit algorithm the transformer is running. The quality, the statistical properties, the number of examples, they directly control the computation being performed.
So prompt engineering is basically data set curation for this internal algorithm.
In a very real sense, yes. And finally, fourth, architecture matters algorithmically. Don't just think of depth and width as adding more power. Think of them as algorithmic constraints. Depth enables iteration, like GD or full OLS. Width enables large, direct computations, like matrix manipulations. Your architectural choices shape the kinds of algorithms that can emerge.
Got it. Execute algorithms, beware ode, prompting is steering, architecture shapes the algorithm. That really demystifies things.
It does. But it also leaves us with a pretty deep final thought to consider.
Let's hear it.
If the core mechanism of ICL isn't the abstract general mathematical principle like the idea of OLS that works anywhere, but rather a highly efficient yet brittle computational shortcut, optimized only for the training distribution, what does that imply about the fundamental nature of the intelligence these systems exhibit? How different is that kind of optimized pattern matching from human abstract reasoning, where we seem able to grasp a principle like OLS and apply it robustly, even in situations wildly different from how we first learned it? That gap between the shortcut and the principle feels like a really important open question,